back. This is part 4 of the sensorless FOC bring up chapter. In the previous section, we brought the motor up in open loop using align and go. That gave us a stable startup and confirmed that the motor could spin reliably before moving into closed loop operation. In this section, we'll build on that and bring the motor into closed loop torque mode. I'll first go over closed loop torque mode and review the key estimator settings, then enable torque mode in the GUI, and then finally use JScope in RTT mode to watch the open loop to closed loop handoff. That handoff is one of the most important parts of sensorless FOC bring up because this is where control transitions from the forced startup angle to the estimator angle. In open loop, the startup routine is forcing the motor angle so that the rotor can begin moving. But once the motor reaches the right operating region, the estimator starts taking over and provides the angle and speed used for closed loop control. So in this section, the main goal is to not just enable closed loop. The goal is to make sure the estimator locks in properly and that the transition happens smoothly. If that handoff is clean, the motor continues running smoothly in closed loop. If it's not, the motor may jerk, become noisy, or even lose synchronization. But before enabling closed loop torque mode, we need to make sure the estimator settings are in a good starting range. The key settings here are the observer bandwidth, the damping factor, the speed filter cutoff, and the angle correction. These values affect how well the estimator tracks the rotor and how stable the transition into closed loop will be. First is the observer bandwidth, or BW. This controls how quickly the estimator responds to changes in the motor. A common starting point is around 2 times the nominal speed, and in general, it can fall somewhere between 1 and 4 times nominal speed. If the bandwidth is too low, the estimator may respond too slowly. If it's too high, it may become noisy or less robust. So for initial bring up, I would like to start with a reasonable conservative value and only adjust it if the transition is not behaving the way I want. Next is the damping factor, or DF. For initial bring up, the default value is usually a good starting point. Next is the FOC speed, which is the speed filter cutoff frequency. This should be chosen based on the type of motor and application. Higher dynamic systems can usually use a higher cutoff. Slower systems often need a lower cutoff for smoother speed estimate. So this value is really balancing responsiveness against noise. Next is the angle correction offset and gain factor. These are tuning parameters that can help optimize estimated angle later on, but for initial bring up, I recommend leaving them at 0 and focusing first on getting a clean transition. Let's head over to the FOC GUI and I'll show you my motor setup. Here is the FOC GUI. Here you can find under the tuning and pause tabs, you can find the LBG1 estimator section. Here you can find all the estimator settings. For bandwidth, I have it at 1500. This is automatically calculated because I have the auto bandwidth checkbox enabled. KP and KPI are both non-zero, so this is fine. The angle correction, I'll start with 0 for the offset and 0 for the factor. And the FC back EMF mag, let's keep this at 100. Okay, so those are the estimator settings. Okay, so to enable closed loop torque mode, you first go to the FOC GUI. Under the align and go, there is a checkbox closed loop auto. You will check this box. Once you check this box, the following parameters are then considered: ID ref closed loop and IQ ref closed loop. You want to also make sure the closed loop mode is set to torque mode. I can show you in the GUI. There's torque mode and speed mode. Make sure it's in torque mode. Now for the recommended values for ID ref closed loop and IQ ref closed loop. For ID, set to 0 for the tuning process, and IQ ref, set this to 10% of your max current. So we'll set this to 0. IQ ref set this to 10% of your maximum current. My maximum current is 8 amps. Then I can set to 0.8 for now. Let's go ahead and write all parameters. Okay, so to observe the transition more clearly, I'm going to use JScope. I'll quickly go over how to enable JScope RTT mode. There is a guide in our resources folder on how to do this, but I'll go ahead and do this live. You will go to the FOC firmware under the config debug.h file, which is also shown here. You will first make sure line 28 is enabled and also line 35. This is for RTT mode. So in RTT mode, the FOC GUI lets me assign 4 debug outputs using DAC 1 through DAC 4. And that is in the GUI. If you go to the debug here and go to DAC, there's 4 DAC outputs. These 4 selected variables are then streamed in real time to JScope. This is especially useful here because I can directly see what happens during the transition from open loop to closed loop. Go ahead and build and re-download your firmware to your device. And now we're going to open JScope. JScope it should be in the JLink installation folder. So you'll first be prompted with creating a new project and start JScope. Specify which device you're using. I'm using a PAC 55 724. You can use any PAC 55 device as long as you're using the correct core. It's a Cortex M4, so I can use any of these. Let's just use 5524. Next, we will select the target interface. Make sure it's in SWD. We will keep the interface speed at 4000. Sampling source, again, we're using RTT mode. Next, click OK. It will show you this message. You will click OK. And here is JScope. To use this, you first need to select the variables on the GUI. For this demo, I'll use 4 signals. For DAC output 1, I'll use the open loop angle. Open loop ideal angle, number 6. For the DAC output 2, I'll use estimated angle. And for DAC output 3, I'll use the IQ reference, number 3. And then we can also show the phase current, which is, in this case, I alpha. Okay, so let's write all parameters. I'll try to show both windows side by side. First thing is you will click play to start sampling. So we can also go ahead and stop sampling, and this will pause it, and then we can zoom in and take a closer look. So let's first start off with press play. Make sure you're at least at 20 seconds per division so you can get a bigger scope of what's going on. Make sure closed loop is checked. We will do our first attempt in closed loop. So let's get started. Okay, so I do see the motor spinning very fast. Do see a message saying PWM duty cycle is saturated. So what I'm going to do is decrease the current. So now the speed has slowed down. We will slow it down even further. So the motor is still spinning much slower. You can see that from the currents. So the motor is still spinning. And let's go ahead and take a closer look at JScope by first disabling the motor. Motor is stopped. Let's stop JScope sampling. Now let's zoom in. Okay, so I'll zoom in at the beginning. So first you'll see the DC alignment we had for 1 second. So this is 1 second here. Then it will be in the align and go startup mechanism, where we give it a forced angle. So what I do want to show you here, this right here, this is the critical transition point. Here the firmware is handing control from the startup generated angle over to the estimator. The angle traces line up cleanly, and speed feedback remains stable without a large disturbance. You can see that it could be improved. You can see the open loop angle is the red. The blue, you can also change colors here. So from here, you can see the open loop angle is in the red. Orange is the estimator angle. And phase current is the yellow. Let's move this down. You can move the signals by clicking on this little triangle on the farmost left side. Same thing for the green. Green is the IQ reference. This is what a OK handoff looks like. The angle traces do come together, and the motor keeps running without a strong jerk, isolation, or a loss of sync. I don't see any current spikes. We can give it another try just to see if it's reliable. Let's go ahead and motor enable. So it's running slower this time, which is a good speed. Let's disable the motor and then go to JScope. It does start reliably. That's a good start. So yeah, this is what a good transition looks like. Okay, so now let's go over a few common transition behaviors to look for and what adjustments to try if the handoff is not clean. So the general order I recommend is this. First, always verify open startup. Second, adjust bandwidth if the estimator is not tracking well. Third, adjust the FOC speed, also known as the speed cutoff frequency. This is if the speed estimate looks too noisy or too sluggish. And only after that, fine-tune angle correction if the motor is already running but still needs optimization. And just like in open loop tuning, I recommend changing one variable at a time so it is clear what effect each adjustment is having. The most important thing to look for is smooth convergence between startup angle and the estimator angle, followed by a stable handoff with no harsh disturbances. Once that looks good, you have a solid starting point for further closed loop tuning.